Hey everyone, welcome back to Developer. Today in this video I am going to be showing you guys a neat little RAII trick to automate arbitrary resource management. By this we would be ensuring that nothing goes wasted and we never leak any resources. So let's get started. Here I have a simple hello world application. If we run this, prints hello world onto the screen, nothing really special. Let's suppose if we have a function, let's have the return type as void. Let's name the function as func. We'll take no parameters for now. We'll see if we can add it later on. Let's allocate some memory on the heap. Let's allocate a bunch of ints. Int pointer array equals new int. Let's allocate 100 ints. Now let's do something with this. Let's initialize this array. For int I equals 0, I less than 100, I plus plus. Array I equals I plus 1. Well, nothing really fancy. We're just creating an integer array of size 100 and we are initializing it from 1 to 100. This integer pointer is a heap allocated memory, and well, we are allocating memory which we might forget to release later on. So let's ensure that we do not do that and delete our array once we are done with it. Delete array. Okay, so there you go. That's it. We initialize a bunch of ints and then we delete that array. Let's get rid of this line and call our function func. Let's also just loop over the array and print out the elements once. If we run this, we see a bunch of ints getting printed. Now the function func which we have written ensures that we free the memory once we are done with using that particular block of memory, the array in fact, and well, we never really have any kind of resource leakage going on anywhere. But what if we have, instead of this simple example, we are calling a specific risky function which might throw an exception somewhere in between, or there might be some condition based on which we might need to return earlier, and probably our function might have multiple exit paths, not just this linear kind of situation going on over here. We might have some parameters taken inside of this func which might cause us to lead to move to other branches inside of it, and then we might exit early and not on this particular line over here. We might instead return early and we might never even get any chance to call the delete array line of code. What do we do in this kind of situations? Well, let me first override the delete operator so that we can see the memory being freed. We can do so by overwriting the delete array operator like this. We'll take in a void pointer for memory, the one which needs to be freed. We'll call free on that particular block of memory, and then we can log to the console memory freed. Let's run this now and see what we get. Okay, so a bunch of ints and memory freed printed at the end. So now that we have overridden the delete operator, delete array version of the delete operator specifically, we can actually understand when the memory gets freed. Let's also wrap our func call inside of a try catch block. Here we can catch any kind of exception by providing an ellipsis, and we can just log errors, exceptions rather. Well, obviously in a real program you would be catching individual exceptions properly, so you would be writing something like const stt maybe runtime error, or maybe bad cast, or anything. You can see a number of exceptions being shown to me. Let's just assume for now we are catching all the exceptions in this block. Now what if we throw some exception before we even get to print our array, and obviously before we delete an array? Well, this could be caused because of some function which we might be performing inside of it. This can be inside of another function, maybe void another func which just, well, throws this, and we might be calling this another func. Let's assume for a while that this is a function which is possibly capable of throwing some kind of exception, and we might get this exception thrown when we are calling this another func inside our func. So we might possibly never even get the chance to delete or call the delete array operator on our array. So let's actually see what happens. So if the memory is getting freed, then we would be getting memory freed getting printed on the console, and if not, if we are leaking memory, if we are never calling this delete array line, then we won't get any such log line. Let's see what happens. So if I clear this, run this again, we just see exceptions caught getting printed. We don't see memory freed getting printed. So we successfully leaked memory. Well, just for the sake of this example, let's throw the exception manually. Well, we can understand that there can be situations in which we need to throw exceptions, and possibly this func is might be calling some function which is another func, and it might contain some implementation which not always throws exception but can in some scenarios. So we have simulated another func throwing some exception, and we saw that we were never freeing this memory and we leaked the memory. How do we ensure that the memory is never leaked? Well, we can write something known as a scope guard. A scope guard is a simple wrapper class which takes in nothing but a function, and that function would be responsible for cleaning up of your memory. What we'll be doing inside of a scope guard is tying the lifetime of all the resources in that scope with that scope guard. So the scope guard will be sharing the scope of all the resources which needs to be cleaned up at the end of the scope, and will be cleaning up all of these memories inside of the function which we register with the scope guard class. So let's write a scope guard class. Can write the scope guard like this, public scope guard. Let's take in a function which returns nothing, takes in nothing because we'll be doing some cleanup inside of it. Cleanup func will initialize a member variable cleanup func. Will std move this for now. Don't bother about what std move means, we'll get to it later. There are a lot of things which we need to discuss. There are a lot of things which C++ has. It's a mystery box, and we'll surely be covering all of those in the future in this series. So stay tuned to the channel for that. So what I have done over here is we are taking in a cleanup function, and we are initializing our member variable cleanup function with the cleanup function which was provided during initialization. I'll obviously need to include functional, and in the destructor we'll be calling the cleanup function just like that. Well, don't worry too much about what std move is. We'll get to it when we discuss move semantics and in detail std move. For now, just understand that cleanup function can be not just a typical ordinary function, but most likely a lambda with some captures. So we do not want to copy the captures, and that is why which are bound to the lambda obviously, and so we are trying to move the cleanup function in the scope of this scope guard inside of this mCleanup func. That's the reason behind using std move over here. That's a simple scope guard which we just wrote over here. Now let's sprinkle this scope with a scope guard. We'll call it guard, and we'll provide a cleanup function in the form of a lambda over here. Well, let's put this after the array because we need for our cleanup. What we'll be doing is calling delete on our array. That's it. That's our scope guard declared. So now what will happen? Array and guard objects, they share the same scope. In the case another func or any other function throws any kind of exceptions, the stack unwinding process would begin. What we are doing over here is relying on the stack unwinding process, call in our destructor of the scope guard, which actually calls the cleanup function and gets rid of the array eventually. Alright, so that's the scope guard declared. What we have done essentially is tie the lifetime of array and scope guard together inside of one scope, and if the exception is getting thrown inside of another func, well, in this scenario it will always throw an exception. We ensure that stack unwinding process takes care of calling the destructor on guard, the scope guard instance, and we call our lambda and we free the memory which we allocated over here. So let's build and run this, and we see memory freed and exceptions caught. So we cleanly prevented ourselves from leaking any kind of memory. Well, that was it, folks. That's how ScopeGuard can be used to protect yourself against memory leaks or resource leaks in general. Make sure to check out the source code in the description down below to see an example of managing a C file handler using the ScopeGuard class we just created. Alright, so now that's it for this video. I'll see you in the next video. Make sure to like this video if you learned something new, share this video, and do not forget to subscribe to the channel. I'll see you in the next video. Till then, keep on learning, keep on growing, and keep making mistakes. Bye bye.